Today we are looking at implicit differentiation. Our learning objectives will be implicit differentiation of multivariable functions, use partial derivatives for implicit differentiation, and apply to quadratic, Cobb-Douglas, and logarithmic and linear functions. So suppose that we had a function which is z is equal to a function of x and y. If we were going to find dy by dx of this function, what we would have to do is do the partial derivative of this function with respect to x, that should be there, divided by the partial derivative of this function with respect to y, and then add a negative sign to that. And this is our formula for finding the derivative of an implicit function. If we then had a function with three variables, so a function of x, y, and z, if we were to find the partial derivative of the function with respect to x, if we were going to find the rate of change of z with respect to x partially, we would have to do the function partially differentiated with respect to x divided by the function partially differentiated with respect to z. And then, as you can see, if we were doing the rate of change of z with respect to y, it would be the function partially differentiated with respect to y divided by the function partially differentiated with respect to z, and then a negative sign. So what you should notice is that this x is at the bottom and it's at the top of our fraction over here, and this y is at the top and it's at the bottom of our function. So it's all ways sort of switching around. Cool. If we now look at some examples, here we've got a linear function. A function of x and y is equal to 3x plus 5y, and we've given it the value 20. If we find dy by dx, we will have to do this. So just writing down the formula which was above over here. And when we partially differentiate this function with respect to x, we just get 3. And then partially differentiating with respect to y, we just get 5. So we get minus 3 over 5 for our linear function. If we now had a quadratic function and we were finding dy by dx, again, same thing, we're going to partially differentiate the function with respect to x and then partially differentiate it with respect to y. So when we do that, we get minus 2x plus 2y. That minus is just from the formula. And then we get 2x plus 2y. So just to walk you through that, x squared differentiates to 2x, and then 2xy, if we treat y as a constant and differentiate 2x, we just get 2, so we're just left behind with 2y. And if we differentiate this function partially with respect to y, x squared is just a constant, so it just turns into 0. Over here, we're left behind with 2x, and then when we differentiate this with respect to y, we just get 2y. Cool. So we can see that these two are the same, so we just get minus 1. If we now had a Cobb-Douglas function, so we have k, which usually stands for capital, to the power of something, in this case a half, and then labor to to the power of something, which in this case is also a half, because they need to add up to 1. And that is equal to some quantity which we've labelled as QO. If we work out dL by dk, so the change in labour with respect to capital, we get the function differentiated with respect to k partially over the function differentiated partially with respect to L. When we do this, we get a half k to the minus a half and L to the half over k to the half and then a half L to the minus half. If we now simplify this, these two halves cancel out and we get k to the minus a half L to the half all over k to the power of a half and then L to the minus a half. And so if we have L to the power of a half divided by L to the minus a half, that is the same as doing L to the half divided by L to the minus a half, which is just L to the power of a half minus a half. So we just get L to the power of 1. So we get L and then k to the minus a half all over k to the half is equal to k to the minus a half divided by k to the half, which is k to the power of minus a half, which is just k to the minus 1, which we can write as 1 over k. So we get k at the bottom. So we get minus L over k. With a logarithmic function now, we have a utility function which has variables x and y, and the function is a ln x plus b ln y is equal to some level of utility which we've called u1, and we need to find dy by dx. So we have to do the utility function differentiated partially with respect to x, and then divided by the utility function partially differentiated by y. And so we get a over x divided by b over y. And so this is just a over x divided by b over y, which is equal to minus ay over bx. Cool. If we have a free variable function now, if we now have this free variable function given f, which is a function of x, y, and z, which is equal to x squared plus y squared plus z squared, which equals 1, we are going to find the partial derivative of z with respect to x holding y constant first. In order to do this, we will have to do partial derivative of the function with respect to x divided by the partial derivative of the function with respect to z, and negative. So when we do this, we get 2x over 2z, which is just minus x over z. If we were going to find the partial derivative of z with respect to y, so this time keeping x constant, we will have to do partial derivative of the function with respect to y, and then the partial derivative of the function with respect to z. So we get minus 2y over 2x, which is the same as minus y over x. Cool. If we now look at a more complete question, so something that we might see in an exam, a consumer maximized utility subject to a budget constraint. Their utility function is utility, which is a function of x and y, is equal to x to the power of 0.5 and y to the power of 0.5. So we have a Cobb-Douglas function subject to the budget constraint 2x plus 4y is equal to 40. So we just have a linear budget constraint. If we treat the budget constraint as an implicit equation, find dy by dx. So if we're treating it as an implicit function, we would have to do minus partial derivative of the function with respect to x all over partial derivative of the function with respect to y. So that gives us minus 2 over 4, which is just minus a half. Of course, this is just a linear function, so what we could have done is first divide everything by 2, so we get x plus 2y is equal to 20, and then make y the subject, so we get 2y is equal to minus x plus 20, and then y is equal to minus a half x plus 10. So as we can see, the gradient, which is dy by dx, is minus a half. If we now calculate the gradient vector of the utility function, in order to do this, we just have to work out the partial derivatives of the utility function. So partial derivative of the utility function with respect to x and then with respect to y. So when we do that, we get 0.5 x to the minus 0.5 and then y to the power of 0.5 and then comma 0.5 x to the power of 0.5 and then y to the power of minus 0.5. Part C is now asking us to write down the Lagrangian for this constraint optimization problem. So I haven't yet gone through this in our videos, but I will do it anyways. So the Lagrangian has the form of the function that we want to maximize and then plus lambda of the constraint, which in a general form I will write as g of xy. So if we now substitute everything in, our utility function is, or the function that we want to maximize is x to the power of 0.5 and then y to the power of 0.5 plus lambda, our budget constraint, which is 2x plus 4y minus 40. Cool. If we now calculate the gradient of the Lagrangian, in other words, find out the first order conditions and solve for the optimum values, we have to partially differentiate the Lagrangian with respect to x, y, and then lambda. So first, if we do it with x, we get 0.5, x to the power of 0.5, and then y to the power of 0.5, plus 2 lambda. Cool. So we get this, and our first order conditions are always equal to 0. So if we now solve these two equations to figure out what lambda is, we can do 2y is equal to minus 0.5 x minus 0.5 y power of 0.5, and then 4y is equal to minus 0.5 x to the power of 0.5 and then y to the power of minus 0.5. If we now times this equation by 2, so that we get 4y over here, and then equate the two sides together, we will get minus x to the power of minus 0.5, y to the power of 0.5 is equal to minus 0.5 x to the power of 0.5 and then y to the power of minus 0.5. Hopefully you can see how I did that. If we divide by the minus, we just get pluses on both sides. And then if we divide this side by y to the power of minus 0.5, and then this side by x to the power of minus 0.5, we get y is equal to 0.5x. If we now substitute this equation back into our constraint, which was 2x plus 4y is equal to 40, substituting y into here, we get 2x plus 4 brackets 0.5x is equal to 40. So 2x plus 2x is equal to 40. So 4x is equal to 40. So x is equal to 10 and y is equal to 5. And so lambda, if we substitute it into one of these equations, we get lambda is equal to minus 1 over 4 brackets 10 to the power of minus 0.5 and then f to the power of 0.5. So we get lambda is equal to 1 over 4 times 1 over root 10 times root 5, which is minus root 2 over 8. Cool. Hopefully that all made sense and you know a bit more about implicit differentiation. Make sure to check out the link in the description so that you can buy me a coffee. Thank you very much.